I usually like to start a lecture with something new, but this time I'm going to make an exception and start with the finishing up of Friday because it involves a little more practice with complex numbers, and I think that's what a large number of you are still fairly weak in. So to briefly remind you, it will be sort of self-contained, but still it will use complex numbers, and I think is a good way to start today. So remember, the basic problem was to solve something with where the input was sinusoidal in particular. The k was on both sides, and the input looked like cosine omega t. And the plan of the solution consisted of transporting the problem to the complex domain. So you look for a complex solution, and you complexify the right-hand side of the equation as well. So cosine omega t becomes the real part of this complex function. The reason for doing that, remember, was because it's easier to handle when you solve linear equations. It's much easier to handle exponentials on the right-hand side than it is to handle sines and cosines, because exponentials are so easy to integrate when you multiply them by other exponentials. So the result was, after doing that, y tilde turned out to be 1, after I scaled the coefficient, 1 over 1 plus omega over k. And then the rest was e to the I times omega t minus phi, where phi had a certain meaning. It was the arctangent of, it was a phase lag. And this was then, I had to take the real part of this to get the final answer, which came out to be something like 1 over the square root of 1 plus the amplitude 1 omega k squared, and then the rest was cosine omega t plus minus phi. It's easy to see that that part is the real part of this. The problem is, of course, you have to convert this. Sorry, this should be I omega t. In which case, you don't need the parentheses either. So the problem was to use the polar representation of this complex number to convert it into something whose amplitude was this and whose angle was minus phi. Now, that's what we call the polar method, going polar. I'd like now, for the first few minutes of the period, to talk about the other method of the Cartesian method. I think for a long while, many of you will be more comfortable with that anyway, although one of the objects of the course should be to try to get you equally comfortable with the polar representation of complex numbers. So if we try to do the same thing going Cartesian, what's going to happen? Well, I get to the same point here. So the starting point is still y tilde equals 1 over, sorry, this should have an I here, 1 plus I times omega over k, e to the I omega t. But now what you're going to do is turn this into its Cartesian, turn both of these into their Cartesian representations as a plus ib. So if you do that Cartesianly, of course, what you have to do is the standard thing about dividing complex numbers or taking their reciprocals that I told you at the very beginning of complex numbers. You multiply the top and bottom by the complex conjugate of this in order to make the bottom real. So what does this become? This becomes 1 minus I times omega over k divided by the product of this and its complex conjugate, which is the real number 1 plus omega over k squared. So I've now converted this to the a plus bi form. I have also to convert the right-hand side to the a plus bi form. So it will look like cosine omega t plus I sine omega t. Having done that, I take the last step, which is to take the real part of that remember, the reason I want the real part is because this input was the real part of the complex input. So once you've got the complex solution, you have to take its real part to go back into the domain you started with, the real numbers from the domain of complex numbers. So I want the real part is going to be, the real part of that is, first of all, there's the factor out in front. Let's put that, since that's entirely real, let's put it out in front so it doesn't bother us particularly. And now, I need the product of this complex number and that complex number, but I only want the real part of it. So I'm not going to multiply it out and get 4 terms. I'm just going to look at the 2 terms that I do want. I don't want the others. All right, the real part is cosine omega t from the product of this and that. And the rest of the real part will be the product of the 2 I terms, but it's I times negative I, which makes 1. And therefore, it's omega over k times sine omega t. Now, that's the answer. And that's the answer to, they must be equal unless there's a contradiction in mathematics. But it's extremely important, and that's the other reason why I'm giving you this, that you learn in this course to be able to convert quickly and automatically things that look like this into things that look like that. And that's done by means of a basic formula which occurs at the end of the notes for reference, as I optimistically say, although I think for a lot of you it will not be referenced, but stuff that in the category of, yeah, I think I've vaguely seen that somewhere, but, well, we never used it for anything. Okay, you're going to use it all term. So the formula is the famous trigonometric identity, which is, so the problem is to convert this into the other guy. And the thing which is going to do that, enable one to combine the sine and the cosine terms, is the famous formula that A times the cosine, I'm going to use theta because to make it as neutral as possible. So theta you can think of as being replaced by omega t in this particular application of the formula, but I'll just use a general angle theta, which doesn't suggest anything in particular. So the problem is you have something which is a combination with real coefficients of cosine and sine, and the important thing is that these numbers be the same. In practice, that means that the omega t, you're not allowed to have omega 1. You're not allowed to have omega 1t here and some other frequency, omega 2t here. That would correspond to using theta 1 here and theta 2 here. And though there is a formula for combining that, nobody remembers it, and it's, in general, less universally useful than the first. If you're going to memorize a formula and learn this one, it's best to start with the ones where the 2 are equal. That's the basic formula. The others are variations of it, but there's sizable variations. All right, so the answer is that this is equal to some other constant, real constant, times the cosine of omega theta. Theta minus phi. Of course, most people remember this vaguely. What they don't remember is what the c and the phi are, how to calculate them. I don't suggest you memorize the formulas for them, but you can if you wish. Instead, memorize the picture, which is much easier. Memorize that A and B are the 2 sides of a right triangle. Phi is the angle opposite the B side, and C is the length of the hypotenuse. Okay, that's worth putting up. I think that's a pink formula. It's even worth 2 of those, but I'll thrift. Now, let's apply it to this case to see that it gives the right answer. All right. So to use this formula, how will I use it? Well, I'll reproduce the left-hand side, so that part I just copy. And now how about the right? Well, the amplitude, it's combined into a single cosine term, whose amplitude is, well, the two sides of the right triangle are 1 and omega over k. The hypotenuse in that case is going to be, well, why don't we write it here? So we have 1 and omega over k. And here's phi. So the hypotenuse is going to be the square root of 1 plus omega over k squared. And that's going to be multiplied by the cosine of omega t minus this phase lag angle, phi. You can write, if you wish, phi equals the arctangent of, but you're not learning a lot by that. Phi is the arctangent of omega over k. That's okay, but it's true. But notice there's cancellation now. This over that is equal to what? Well, it's equal to this. And so when we get in this way, by combining these two factors, one gets exactly the same formula that we got before. So as you can see, in some sense, there's not, if you can remember this trigonometric identity, there's not a lot of difference between the two methods, except that this one requires this extra step of the answer will come out in this form, and you then, to see what it really looks like, really have to convert it to this form, the form in which you can see what the phase lag and the amplitude is. It's amazing how many people who should know this includes working mathematicians, theoretical mathematicians. It includes even possibly the authors of your textbook. I'm not sure, but I've caught them in this too, who, in this form, everybody remembers that it's something like that. Unfortunately, when it occurs as the answer in an answer book, and the numbers are some colossal mess here plus some colossal mess here, and theta is, again, a real mess involving roots and roots, cube roots, and whatnot. The only thing is these two are the same real mess. That amounts to just another pure oscillation with the same frequency as the old guy had, and with the amplitude changed and its phase lag, and its phase with a phase shift, moved to the right or left. So this is no more general than that. Notice they both have two parameters in them. These two coefficients, this one has the two parameters in an altered form. Okay, well, I wanted, because of the importance of this formula, I wanted to take a couple of minutes out to proof of the formula. Just to give you a chance to stare at a little more. Now, there are 3 proofs I know. I'm sure there are 27. Like, the Pythagorean theorem now has several hundred. But there are 3 basic proofs. There is the one I will not give you, I'll call the high school proof, which is the only one normally finds in books, physics textbooks or other textbooks. The high school proofs takes the right-hand side, applies the formula for the cosine of the difference of two angles, which it assumes you had in trigonometry, and then converts it into this. It shows you that once you've done that, that A turns out to be C cosine phi, and B, the number B is C sine phi, and therefore it identifies the two sides. Now, the thing that's of course correct, and it's the simplest possible argument. The thing that's no good about it is that the direction in which it goes is from here to here, Well, everybody knew that. If I gave you this and told you write it out in terms of cosine and sine, I would assume and dearly hope that practically all of you could do that. Unfortunately, when you want to use the formula, it's this way you want to use it in the opposite direction. You're starting with this and want to convert it to that. Now, the proof, therefore, will not be of much help. It requires you to go in the backwards direction and match up coefficients. It's much better to go forwards. Now, there are two proofs that go forwards. There's the 1802 proof. Since I didn't teach most of you 1802, I can't be sure you had it. So I'll spend 1 minute giving it to you. What is the 1802 proof? It is the following picture. Picture. I think this requires deep colored chalk. This is going to be pretty heavy. All right. First of all, the A and the B are the given, so I'm going to put in that vector. So there is the vector whose sides are, whose components are A and B. I'll write it without the I and J, and just in this. I hope you had from Jerison that form for the vector. If you don't like that, write AI plus BJ. Okay. Now, there's another vector lurking around. It's the vector, the unit vector, whose I'll write it this way: U because it's a unit vector, and theta to indicate that its angle is theta. Now, the reason for doing that is because you see that the left-hand side is a dot product of two vectors. The left-hand side of the identity is the dot product of the vector AB with the vector whose components are cosine theta and sine theta. That's what I'm calling this unit vector. It's a unit vector because cosine squared plus sine squared is 1. Now, all this formula is saying that the scalar product, the dot product of those two vectors, can be evaluated, if you know their components, by the left-hand side of the formula. And if you don't know their components, it can be evaluated in another way, the geometric evaluation, which goes, what is it? It's the magnitude of one times the magnitude of the other times the cosine of the included angle. Now, what's the included angle? Well, theta is this angle from the horizontal to that unit vector. This is the angle phi is this angle from this picture here. And therefore, the included angle between u theta and my pink vector is theta minus phi. That's the formula. It comes from two ways of calculating the scalar product of the vector whose coefficients are A, B, and the unit vector whose components are sine theta, cosine theta, and sine theta. All right, well, we should, that was 1802. There must be an 1803 proof also. Yes. What's the 1803 proof? The 1803 proof uses complex numbers. It says, look, take the left side, instead of viewing it as the dot product of two vectors, there's another way. You can think of it as the part of the product of two complex numbers. So the 1803 argument, really the complex number argument, says, look, multiply together A minus BI and the complex number cosine theta plus I sine theta. There are different ways of explaining why I want to put the minus I there instead of I, but the simplest is because I want, when I take the real part, to get the left-hand side. I will. If I take the real part of this, I'm going to get A cosine theta plus B sine theta because of negative I and I make 1. Multiplied together. All right. That's the left-hand side. And now the right-hand side, I'm going to use polar representation instead. What's the polar representation of this guy? Well, if AB has the angle theta, then A negative B, A minus BI, goes down below. It has the angle minus phi. So this has magnitude in its polar representation. Its magnitude is A squared plus B squared. And its angle is negative phi, not positive phi, because of this. A minus bi goes below the axis if A and B are positive. So it's e to the minus I phi. That's the first guy. And how about the second guy? Well, the second guy is e to the I theta. So what's the product? It is a squared plus b squared, the square root, times e to the I times theta minus phi. And now, what do I want? The real part of this, and I want the real part of this. So let's just say, take the real parts of both sides. If I take the real part of the left-hand side, I get a cosine theta plus b sine theta. If I take the real part of this side, I get square root of a squared plus b squared times e times the cosine, that's the real part, right, of theta minus phi, which is just what it's supposed to be. Well, with three different arguments, I'm really pounding the table on this formula. But I think there's something to be learned from at least two of them. And, you know, I'm still, for a while, I'll never miss an opportunity to bang complex numbers into your head, you know. Because in some sense you have to reproduce the experience of the race. As I mentioned in the notes, it took mathematicians 300 or 400 years to get used to complex numbers. So if it takes you 3 or 4 weeks, that's not too bad. Now, for the rest of the period, I'd like to go back to the linear equations and try to put in perspective and summarize and tell you a couple of things which I had to leave out, but which are, in my view, extremely important. And up to now, I don't want to leave you with any misapprehension. So I'm going to summarize this way. I'm going, whereas the last lecture I went from the most general equation to the most special, I'd like to just write them down in the reverse order now. So we're talking about the basic linear equations. First order, of course. We haven't moved into second order yet. So the most special one, and the one we talked about essentially all the previous two times, or the last Friday anyway, was the equation where the k is constant. The coefficient of y is constant, and where you also get it on the right-hand side, quite providentially. So this is the most special form, and it was the one which governed what I'll call the temperature concentration model, or if you want to be grown up, the conduction diffusion model. Conduction diffusion, which describes the processes which the equation is modeling, whereas these simply describe the variables, the things which usually you're trying to calculate when you use the equation. Now, there are a class of things where the thing is constant, but where the k does not appear naturally on the right-hand side. And you're going to encounter them pretty quickly in physics, for one place. So I better not try to sweep those under the rug. Let's just call that Q of t. And finally, there's the most general case where you allow k to be non-constant. That's the one we began when we talked about the linear equation, and you know how to solve it in general by a definite or an indefinite integral. Now there's one other thing which I want to talk about. I'll do all these in a certain order, but from the beginning you should keep in mind that there's another, between the first two cases, there's another extremely important distinction, and that is as to whether k is positive or not. Up to now, we've always had k positive, so I'm going to put that here. So it's understood when I write these that k is positive. I want to talk about that too. But first things first. The first thing I wanted to do was to show you that the first case, the most special case, does not just apply to this. It applies to other things too. Let me give you a mixing problem. The typical mixing problem is, it gives another example. You've already done in recitation, and you did one for problem set, the problem of the two rooms filled with smoke. But let me do it just using letters so that you can, the ideas stand out a little more clearly, and you're not preoccupied with the numbers and calculating with the numbers and trying to get numerical examples. So it's the simplest case of mixing. It looks like this. You have a tank, a room, I don't know where everything's getting mixed in. It has a certain volume, which I'll call V. Something is flowing in, a gas or a liquid, and R will be the flow rate in some units. Now, since it can't pile up inside this sealed container, which I'm sure is full, the flow rate out must also be R. And what we're interested in is the amount of salt. So X, let's suppose these are fluid flows, and the dissolved substance that I'm talking about is not carbon monoxide. It's salt, is any dissolved substance, some pollutant or whatever the problem calls for. Let's use salt. So it's the amount of salt in the tank at time t. I'm interested in knowing how that varies with time. Now, there's nothing to be said about how it flows out. What flows out, of course, is what happens to be in the tank. But I do have to say what flows in. Now, the only convenient way to describe the inflow is in terms of its concentration. The salt will be dissolved in the inflowing water, and so there'll be a certain concentration. And as you'll see, for a secret reason, I'm going to give that the subscript E. So E is the concentration of the incoming salt. In other words, in the fluid, how many grams are there per liter in the incoming fluid? That's the data. So this is the data. R is part of the data. R is the flow rate. V is the volume. I think I won't bother writing that down. And the problem is to determine what happens to X of t. Now, I strongly recommend you not attempt to work directly with the concentrations unless you feel you have a really good physical feeling for concentrations. I strongly recommend you work with the variable that you're given, namely the dependent variable is the amount of salt, grams. Well, because it's something you could physically think about. It's coming in, it's getting mixed up, and some of it's going out. So the basic equation is going to be that the rate of change of salt in the tank is the rate of salt inflow. Let me rate salt inflow minus the rate of salt outflow. Okay, at what rate is salt flowing in? Well, the flow rate is the flow rate of the liquid. I multiply the flow rate, 1 liter per minute, times the concentration, 3 grams per liter. That means 3 grams per minute. It's going to be, therefore, the product of the flow rate and the concentration, incoming concentration. How about the rate of the salt outflow? Well, again, the rate of the liquid outflow is R, and what is the concentration of salt as it comes in the outflow? I must use, when you talk flow rates, the other factor must be the concentration, not the amount. So what is the concentration in the outflow? Well, it's the amount of salt in the tank divided by its volume. So the analog of the concentration here is X divided by V. Now here's a typical messy equation. dx dt, let's write it in the standard linear form, plus R times X over V equals R times the given concentration, which is a function of time. Now, this is going to be some given function, and there will be no reason whatever why you can't solve it in that form, and that's normally what you will do. Nonetheless, in trying to understand how it fits into this paradigm, which kind of equation is it? Well, clearly there's an awkwardness in that on the right-hand side we have concentration, and on the left-hand side we seem to have amounts. Now, the way to understand the equation, as opposed to the way to solve it, well, it's a step on the way to solving it. You can, but I emphasize, you can and normally will solve it in exactly that form. But to understand what's happening, it's better to express it in terms of concentration entirely, and that's why it's called the concentration or the concentration-diffusion equation. So I'm going to convert this to concentrations. Now, there's no problem here. X over V is the concentration in the tank. And now, immediately you see, hey, it looks like it's going to come out just in the first form. But wait a minute. How about the X? How do I convert that? Well, what's the relation between X? So, if the concentration in the tank is equal to X over V, so the tank concentration, then X is equal to C times the constant V, and dx dt, therefore, will be V times dc dt. You see that? Now, that's not in standard form. Let's put it in standard form. To put it in standard form, I see now that it's not R that's the critical quantity. It's R divided by V. So it's dc dt, C prime, is plus R divided by V. I'm going to call that K. Kc, no, let's not. R divided by V is equal to R divided by V times CE. That's the equation expressed in form of where the concentration is the dependent variable rather than the salt, amount of salt itself. And you can see it falls exactly in this category. That means that I can talk about it, the natural way to talk about this equation is in terms of the same way we talked about the temperature equation. I said concentration. I mean, that concentration has nothing to do with this concentration. This is the diffusion model where salt outside, salt solution outside, cell in the middle, salt diffusing through a semi-permeable membrane into that, uses Newton's law of diffusion, except he didn't do a law of diffusion. But he's sticky. His name is attached to everything. So that's this concentration model. It's the one entirely analogous to the temperature, and the physical setup is the same. This one is entirely different. Mixing in this form of this problem has really nothing to do with this model whatsoever. But nor does that concentration have anything to do with this concentration, which refers to the result of the mixing in the tank. But what happens is the differential equation is the same. The language of input and response that we talked about in the old is also available here. So everything is the same. And the most interesting thing is that it shows that the analog of the conductivity, the K, the analog of conductivity and diffusivity is this quantity. I should not be considering R and V by themselves. I should be considering as the basic quantity the ratio of those two. Now, why is that? Is the basic parameter. What is this? Well, R is the rate of outflow and the rate of inflow. What's R over V? R over V is the fractional rate of outflow. In other words, if R over V is 1/10, it means that 1/10 of the tank will be emptied in a minute, say. In other words, we've lumped constants into these two constants into a single K, and at the same time have simplified the units. What are the units? This is volume per minute. This is volume, so it's simply reciprocal minutes. Reciprocal time, which was the same units that diffusivity and conductivity had. Reciprocal time. The space variables have entirely disappeared. So in that way, it's simplified conceptually, and now you can answer the same type of questions we asked before about this. I think it'll be better for us to move on, though. Well, just example one, really simple thing. Suppose since we spent so much time worrying about what was happening with sinusoidal inputs, I mean, when could CE be sinusoidal, for example? Well, roughly sinusoidal. If, for example, if some factory were polluting, this were a lake, then some factory were polluting it, but in the beginning, at the beginning of the day, they produced a lot of the pollutant, and by the end of the day, when it wound down, it might well happen that the concentration of pollutant in the incoming stream would vary sinusoidally, with a 24-hour cycle. And then we would be asking, so suppose this varies sinusoidally. In other words, is like cosine omega t. I'm asking how closely does the concentration in the tank follow C sub E? Now, what would that depend upon? Think about it. Well, the answer, suppose K is large. Closely, let's just analyze one case. If K is big. Now, what would make K big? We know that from the temperature thing. If the conductivity is high, then the inner temperature will follow the outer temperature closely. And the same thing with the diffusion model. Well, we, of course, therefore, since the equation is the same, we must get the same result here. Now, what would make K big? If R is big, if the flow rate is very fast, we will expect the concentration of the inside of that tank to pretty match fairly closely the concentration of the pollutant, of the incoming salt solution. Or if the tank is very small. For fixed flow rate, if the tank is very small, well, then it gets emptied quickly. So both of these I think, are intuitive results. And of course, as before, we got them from that by trying to analyze the final form of the solution. In other words, we got them by looking at that form of the solution up there and seeing if K is big, if K increases, what happens to the amplitude and what happens to the phase lag. But that summarizes the two. So this means, closely means that the phase lag is big or small. The lag is small. And the amplitude is, well, the amplitude, the biggest the amplitude could ever be is 1, because that's the amplitude of this. So the amplitude is near 1. 1 because that's the amplitude of the incoming signal, input, whatever you want to call it. Okay, now I'd like to spend the rest of the time talking about the failures of number 1, and when you have to use number 2, and when even number 2 is no good. So let me end first order equations by putting my worst foot forward. Well, I'm just trying to avoid disappointment and misapprehensions for you. I don't want you to leave this room saying, well, he said that, and, you know. Okay. So the first one you're going to encounter very shortly where 1 is not satisfied but 2 is. So on some examples where you need 2. Well, it's going to happen right here. Somebody sooner or later is going to draw on that loathsome orange chalk, which is unerasable. Something which looks like that. Remember, you saw it here first. R. Yeah, we had that. Okay, see, you had it in high school, too. That's a capacitance. This is a resistance. That's an electromotive force, a battery or a source of alternating current, something like that. Now, of course, what you're interested in is the current, how the current flows in the circuit. But since current across the capacitance doesn't make sense, you have to talk about the charge on the capacitance. So Q, it's customary in a circuit this simple to use as the variable not current, but the charge on the capacitance. And then Kirchhoff's, you're also supposed to know that the time derivative of Q is what's called the current in the circuit. That's sort of intuitive. But look, I in a physics class, J in an electrical engineering class, and Y, not the letter Y, but why is that? That is because electrical engineers use lots and lots of complex numbers, and therefore they have to call current J, I guess. I think they do J in physics too now. No, they don't. I don't know. So I is ambiguous if you're in that particular subject, and it's customary to use, I don't know. Now it's completely safe. Okay, where are we? Well, the law is, the basic differential equation is Kirchhoff's voltage law, that the sum of the voltage drops across these three has to be 0. And so it's R times I, which is dq dt. That's the Ohm's law. That's the voltage drop across the resistance. The voltage drop across the capacitance is Coulomb's law, one form of Coulomb's law. It's Q divided by C. And that has to be the voltage drop. And then there's some sign conventions. So this is either plus or minus, depending on your sign conventions, but it's E of t. Now, if I put that in standard form, I probably should say Q prime plus Q over RC equals, well, I suppose E over R. But this is what would appear in the equation, but it's not the natural thing. The K is 1 over RC, and that's the reciprocal. The RC constant is what everybody knows is important when you talk about a little circuit of that form. On the other hand, the right-hand side, it's quite unnatural to try to stick on the right-hand side that same RC. Call this EC over RC. People don't do that, and therefore it doesn't really fall into the paradigm of that first equation. It's the second equation that it really falls into the... Another simple example of this is chain decay, radioactive chain decay, where let's say the substance, radioactive substance A, decays into, let's say one atom of this produces one atom of that for simplicity. So it decays into B, which then still is radioactive and decays further. Okay. What's the differential equation, which is going to be, it's going to cover this situation. What I want to know is how much B there is at any given time. So I want a differential equation for the quantity of the radioactive product at any given time. Well, what's it going to look like? Well, it's the amount coming in minus the amount going out, so to speak. The rate of inflow minus the rate of outflow, except it's not the same type of physical flow we had before. How fast is it coming in? Well, A is decaying at a certain rate, and so it's the rate at which A decays is by the basic radioactive law. It's K1, it's constant, decay constant, times the amount of A present. If I use the differential equation with A here, I'd have to put a negative sign because it's the rate at which that stuff is leaving A. But I'm interested in the rate at which it's coming into B. So it has a positive sign. And then the rate at which B is decaying, and therefore the quantity of B is, good B is gone, that will have some other constant, B. So that will be the equation. And to avoid having two dependent variables in there, we know how A is decaying. It's going to look like, so it's K1, some constant times A will be e to the negative, the decay law, so times the initial amount that was there, times e to the negative K1t. That's how much A there is at any given time. It's decaying by radioactive decay law, minus K2b. Okay, so how does the differential equation look like? It looks like B prime plus K2b equals an exponential, K1A0 e to the negative K1t, but there's no reason to expect that that constant really has anything to do with K2. It's unnatural to put it in that form. And so here, too, is another example where it's the second form, which is the correct one. Now, in the last 2 minutes, I wish to alienate half the class by pointing out that if K is less than 0, none of the terminology of transients, steady state, input, response applies. The technique of solving the equation is identical, but you cannot interpret. So the technique is the same, and therefore it's worth learning. The technique is the same. In other words, the solution will be still e to the negative kt integral q of t e to the kt dt plus a constant times e to the k. Oh, this is terrible. No. dy dt. Let's give an example. The equation I'm going to look at is something that looks like this. Y equals q of t, let's say. Okay? A constant, but the constant A is positive, so the constant here is negative. Then when I solve, my k, in other words, is now properly written as negative A, and therefore this formula should now become not this, but the negative A is, the negative k is AT. And here it's negative AT, and here it is positive AT. Now, why is it, if this is going to be the solution, why is it totally, all those things totally irrelevant? This is not a transient any longer, because if A is positive, this goes to infinity. Or it might go to minus infinity if C is negative. So it's not transient, it's not going to 0, and it depends heavily on the initial condition. That means that of these two functions, this is the important guy. This is just fixed, some fixed function. Everything, in other words, is going to depend upon the initial conditions, whereas in the other cases we have been studying, the initial conditions after a while don't matter anymore. Now, why did I say I would alienate half of you? Well, because in what subjects will A be positive? In what subjects will K be negative? K is typically negative in biology, economics, Sloan. In other words, the simple thing is, think of it in biology. What's the biological equation? What's the simplest equation for population growth? Well, it is dp dt equals some, if the population is growing, a times p, and a is a positive number. That means p prime minus ap is 0. So the thing I want to leave you with is this. If life is involved, k is likely to be negative. K is positive when inanimate things are involved. I won't say dead, inanimate.